Okay, here we are in video 2.2. We're going to talk about taking the elements that we just talked about in section 2.1, the organization of the periodic table in elements based on chemical properties. We're going to think about how those elements can combine to form these things called chemical compounds. So a chemical compound is really pretty straightforward. It's the combination of those individual elements. Remember, elements, the 118 of them, are the simplest basis of all matter in the universe, but we can combine those in virtually an infinite number of ways to create these unique compounds that have their own chemical and physical properties that are different from the individual elements. And so I've got an example of a chemical reaction here, and don't worry if this looks foreign to you, because we haven't talked at all about balancing reactions and what these things mean, and so this is sort of a basic introduction to that. And so what we've got here is this compound here, which we have two, HGO, this is mercury and this is oxygen, combined together to form the solid that we call mercurous oxide. This is a compound, and the HGO is the chemical formula for that compound. If we heat this thing up in a Bunsen burner, which is shown over here in the image to the right, what we can do is get this compound to actually break apart this bond of the compound back into its constituent elements of mercury and oxygen. So you get liquid mercury and oxygen gas, and that's what's being shown in this section of the image. What we need to talk about, though, is that this whole representation is a chemical reaction, and often I shorthand reaction as RXN, so if you see me write that, it means the same thing. And there's something unique about the way that this is represented. When we have a chemical reaction like this, all chemical reactions are going to obey this idea called the law of conservation of matter. And put pretty simply, that just means that this side of the reaction here, which is the reactants, the mass of this, mass of reactants, it has to equal the mass of what we call the products, the things on the right side of this product arrow. So the mass of products has to equal the mass of reactants, and we consider that principle the law of conservation of matter. And that may seem trivial, but it's really important because all of the mass contained in this original reactant is still preserved in the elements that are produced. And this is going to be operative in any chemical reaction that we use going forward. And it's going to be really important because it's a useful tool to help us. If we don't know all of the components of a chemical reaction, we know this has to be true, and it can help us identify what the unknown portions of the reaction are. Another way to phrase the law of conservation of matter that many of us have heard before is that matter cannot be created or destroyed. It can only be converted into different forms, and that's exactly what's happening here. This mercury, these two mercuries are still these two mercuries, and this oxygen times 2 of them is still these 2 oxygens. And so if we were to weigh our reaction vessel, if this was contained inside of this, this glass tube here, we weighed it, then heated it and weighed it again, the masses would be exactly the same. And that's an illustration of the law of conservation of matter. So we know that elements can combine to form these compounds, but how do we think about how the number of elements or the ratio of elements combine to form a single compound? That brings us to this idea of the law of definite proportions, which is a sort of fundamental chemical law that is pretty straightforward, but it requires us to define it. So let's think about the water molecule, which is H2O, right? In H2O, we have 2 hydrogens and 1 oxygen, which means hydrogen itself, and we'll talk about this a little bit, hydrogen itself weighs 1 atomic mass unit, and oxygen weighs 16 atomic mass units. So in 1 molecule of water, we would have 2 hydrogens, which is 2 AMUs, and we would have 1 oxygen, which is 16 AMUs. But what if we had 2 molecules of oxygen? We would have 4 hydrogen, which is 4 AMUs, and how many oxygen atoms would we have? Yeah, pretty straightforward. We would have 2 oxygen atoms, which would be 32 AMUs. And we could sort of go down this path. We could say, what about if we have 8 hydrogen atoms, which would constitute 4 water molecules? This is going to be 8 atomic mass units. How many oxygens will we have? Yeah, similar. We would have 4 oxygens, which would give us a total of 64 AMUs. So the law of definite proportion states that for a given molecule, so for a given compound or molecule, the proportion, the mass proportion of the elements that go into that molecule will always be constant. And so if we look at the ratio here, let's just make a column called ratio here. And let's just say, what is the mass of oxygen to hydrogen? Well, that would be 16 over 2, which is 8. Here we could do the same thing. This would be mass of oxygen, which would be 32 divided by 4, which is 8. And here we could say mass of oxygen is 64 divided by 8, which is also 8. And so law of definite proportion just says that in a particular compound or molecule, those 2 elements can combine, but the ratio of their masses will always be the same for that given molecule. We'll see in just a couple seconds that these 2 elements could combine in different proportions, but then that would give us a different molecule. For a given molecule, if the molecule doesn't change, the ratios will always be the same, and that's the law of definite proportions. Okay, so we know from the law of definite proportions that for a given molecule, the ratio, the mass ratio of the individual elements that constitute that molecule have to always be the same. But I did allude to the fact that elements can combine in different proportions, and we call that a separate fundamental law, the law of multiple proportions here. And so the first example here I have the same as what we had before. Hydrogen gas plus oxygen can make H2O. And in red above it I have the mass. So each hydrogen atom weighs 1 atomic mass unit, so collectively this weighs 2. 1 oxygen atom weighs 16, and so the ratio of oxygen to hydrogen here is going to be the same as it was before in the law of definite proportions, which is 8. If we go to our second example, here we have H2 gas and O2 gas making this new compound H2O2, which is also the same as hydrogen peroxide. So we have a difference here in 2 totally different molecules, but the only difference is the ratio at which the elements are combining. In this case, we have the mass of oxygen as 32 divided by the mass of hydrogen, which is 2, which is 16. And so the law of multiple proportions states that elements can combine in different ways during these reactions, but the mass ratios of these compounds, which we've computed here, these are the mass ratios, they will be whole number ratios of each other. In other words, if we were to take this 16 divided by 8, the ratios of the ratios we would see that the mass ratio of H2O2 is exactly 2, a whole number 2, twice that of the ratio in pure water. So the law of multiple proportions, summarized again, states that elements can combine in different ratios to create wholly different compounds, which is the difference between law of definite proportions, but their ratios, their mass ratios, will always be whole numbers of each other. They'll never be fractional numbers, and that's important. Okay, so we've thought a little bit about how all matter is created by these, or constituted by these elements, these almost 120 elements, but they're the sort of basic unit of matter, and they have unique chemical and physical properties. They can combine together to form compounds that have even different properties from themselves. We also know that they combine in specific proportions based on mass ratios to either give the same or different compounds. That was the law of definite and multiple proportions. But what actually constitutes an element itself, right? That's the basic unit of chemical matter, but we also know that stuff has to make up the atom itself. So that brings us to this idea of atomic structure. So what makes up an atom? We'll have to sift through a couple sort of seminal or key experiments that were done in the last couple hundred years to answer this question. So let's first describe this experiment that we call the cathode ray tube experiment that was done in 1897 by J.J. Thomson. And so I've got an image of a really simple cathode ray tube. And you've all probably seen this before in real life, maybe not this exact tube, but an example of a cathode ray tube is an old TV or computer monitor. And so what happens inside of this tube is we've got this glass tube that is highlighted here, and we pump out all the air. So we put it under vacuum, and we apply a very large voltage between these two poles. And so there's some really tiny wires that are in the tip here and in the tip here. Let's change the color here. You apply this voltage and the tube on the inside is coated with this material that we call phosphorescent. And that's important because phosphorescent materials start to glow like a glow-in-the-dark material when they are struck by a small particle. And so back in the 1900s, this guy, J.J. Thomson, created a tube. It didn't look exactly like this, but something similar. And he did this experiment. And what he saw was that even in vacuum, he could get this sort of arc or this bright line to traverse across this tube. He didn't know what it was, but he could see this line. And so you've got this huge energy difference, and you've got this little arc that goes across this. The really key additional experiment he did was he took just a normal magnet, like a bar magnet, which is being held right here by this person, and he put it up against the cathode ray tube. And what he observed was that sort of arc of brightness from the phosphorescent background or the phosphorescent material coating the inside of the cathode ray tube, it starts to bend based on the presence of this magnet. And so he was able to draw a couple really key conclusions here. One, he said, well, whatever is passing through here, it must be charged because it's interacting with this magnetic field. He was also able to change the size of this field. So he could change the size of the magnetic field, and he could see the shape of this deflection change, which allowed him to get an estimate of both the mass and the charge of this particle. And we know now that what he was getting at with these really early experiments was that the atoms or elements are actually composed of several subatomic particles, one of which is the electron, which has a negative charge. And so this was a really, really early experiment that pointed scientists in the direction that atoms actually aren't the smallest unit of matter, and that they're actually composed of these subatomic particles, electrons being a really key particle when we think about the chemical and the physical properties of those elements. And so we're going to tie that back in a little bit later and think about electrons, reactivity, and ultimately how those elements are arranged in the periodic table. Okay, so following on Thomson's sort of hypothesis that um, elements and atoms of those elements must actually be composed of even smaller subatomic particles, and that there must be some negatively charged particles that are really, really small. Um, Scientists at the time, remember this is around 1900, scientists at the time also noted that all of the solids of these elements that existed around them existed in the neutral state, meaning they didn't shock them when they touch them or observe them. So they also hypothesized then if there is a negatively charged subatomic particle, there must be an equal and opposite positively charged subatomic particle that renders those elements neutral. And so this guy, Ernst Rutherford, came along about 15 years later, and he designed an experiment to evaluate, well, what else is inside of these atoms or these elements. And he set up an experiment that looks like this that I have highlighted here. So he took a very small sample of a radioactive sample at the time, and we don't need to know that much about it, except that radioactive samples, when left to their own devices, they'll spontaneously decay, and when they do that, they emit a bunch of high energy particles that we call alpha particles, these big charged particles. They knew that at the time, but they didn't know much else about what constituted the inside of these atoms. And so he constructed this little lead box here. In this lead box, he used lead because lead is so dense, it doesn't allow these particles to penetrate. That's why you wear lead aprons when, or if you've ever had an x-ray taken of your body over sensitive parts, so that you don't get that penetration of those particles. And so he drilled a really tiny hole in there, he put a sample inside, and then he hung a tiny bit of gold foil in the center of the experiment, maybe 10 or 15 centimeters away. So this is like that gold leaf that you might have seen on like a decorative card, that really, really thin, flaky gold foil. It's thinner than a strand of human hair. And then he surrounded the whole experiment with this photosensitive paper that they call zinc sulfide screen. And the idea is that screen lights up whenever any of these alpha particles collide with it. And so his sort of hypothesis was, well, gold's really dense too, sort of like lead. If anybody's ever held a gold object, it's pretty heavy because it's so dense. And he sort of hypothesized originally that as this beam of alpha particles moves or impinges upon the gold foil, probably a bunch of it's just going to reflect backwards and light up the screen in this half, sort of the former half of the zinc sulfide screen. So he ran this experiment, and of course that's not what he observed. He observed the vast majority, 99.9%, actually went straight through the gold foil and lit up this section of the zinc screen. And this was a big surprise to Rutherford, because he assumed, as I mentioned before, that most of the reflection would occur on this half of the experiment. But in fact, only about 1 in 20,000 particles bounced back. The rest of them all went and collided with the sort of opposite side of the gold foil. Okay, so this left Rutherford in this interesting dilemma, because his original understanding, and really the understanding at the time, this is about 1911, so think about this in context historically, this is, you know, a year before the Titanic sank. This is early times, but really not that long ago for us to not actually know how atoms are constructed. And so he took a step back and he said, well, that must mean that the vast majority of space inside of this gold foil at the subatomic level must be empty space. And that's conflicting to what people had believed up to that point. And so his sort of model that he developed looks something like this, where the vast majority of this gold foil, if we were able to zoom into the subatomic level, the vast majority is empty space, which is all of this space around here. And then in the center of each of these gold atoms are these tiny little dense dots. And those dense dots are where the positive subatomic particles are, this nucleus that contains these protons. And so this was really the very first experiment that put forth this model that said, well, actually most of the space in atoms is empty, and that all of the actual matter and the mass of the atom is centralized right to the center of the core, which gave birth to this idea of the nucleus, and the nucleus containing these things called protons, which are the positive portion of the subatomic particles, and these things called neutrons, which are neutral in charge, but have the same mass as a proton. And we'll talk a little bit more about that in a second. So as a result of Rutherford's model, that essentially equated that dense center of a nucleus to really the size of a pea, we'll make that red, in the center of roughly the volume or the size of this giant stadium. So if you had a pea sitting right down here in the center of this stadium, that's roughly the size of all of the protons and neutrons, where all the mass exists. Everything else was empty space, and that's why all of those alpha particles that were zipping through the gold foil were passing directly through all the way to the other side untouched. And so that gave scientists a completely different understanding of what was happening at the subatomic level. So fast forward a couple years after the experiments of J.J. Thomson, this other scientist Millikan, which we haven't talked about in detail, and Rutherford and other scientists that followed suit were able to take these hypotheses that said that there must be these small particles of negative and positive charge, and they actually went in and figured out exactly what the mass of these particles were and their specific charge. And so what we now know to constitute an atom are these three subatomic particles. The electron, which if you look at the mass, is really, really small. It's about 4 orders of magnitude smaller than the proton and neutron. When I talk about orders of magnitude, I'm talking about these exponential numbers. This is 10 to the minus 28. This is 10 to the minus 24. That's 4 orders of magnitude different. 4 orders, which I'll write as 4 in degree, that's 4 orders of magnitude. That's the same as 10 to the 4th difference, which is the same as 10,000 times different. In other words, protons and neutrons weigh about 10,000 times that of an electron. So that gives you some sort of sense of scale. These are much larger, more dense entities. Electrons are these very, very, very light, small objects. The total charge, though, on every single electron is -1. The total charge on every proton is +1, and the neutrons are just simply mass. They have the same exact mass as a proton, but they are neutral in charge.